Hi friends, I'll start this video by telling you something about resistivity. Resistivity, as you know, is the characteristic of a system and it is constant at a particular temperature, but it varies with temperature in this way. As you see here, rho t is equal to rho naught into 1 plus alpha delta t, where delta t is t minus t naught. And here rho naught and t naught are your reference values. T naught is your reference temperature, and the alpha that you see here, it is the temperature coefficient of resistivity. Units per temperature. Now, seeing this equation, you may expect the graph of rho t versus temperature to be a straight line, right? But actually it's not, because this rho naught itself is a function of temperature. So it's not a straight line, but if you are dealing with temperatures which are near to your reference temperature T naught, then in this range you can approximately say that the graph of rho t versus t is a straight line. And let me tell you one more thing. You know that the formula for resistivity is 1 by sigma, where sigma is the conductivity. And you also know that conductivity can be expressed as n e squared tau by m. So I'll write this as this thing, where m is the mass of electron, e is the charge, the basic unit of charge, 1.6 into 10 power minus 19, and n is the number of electrons per unit volume. Tau is the relaxation time, I mean the time between two consecutive collisions that takes place in the metal conductor or whatever it is. So when you increase the temperature, the electrons in the conductor move even more fastly, right? So you expect this tau, the time constant between two collision, to reduce, and hence you expect the rho to increase, because n is pretty much constant for metals. It doesn't change with temperature. So the resistivity increases with increase in temperature for conductors. Whereas in semiconductors or insulators, even there the tau decreases with the increase in temperature, but there what happens is the number of electrons per unit volume, it considerably increases with increase in temperature, and this increase compensates the decrease in tau. Hence totally I can say that the resistivity decreases with increase in temperature for semiconductors or insulators. Let's move forward. Let us solve a small problem. You have an electric toaster which uses nichrome as its heating element. Now, it's given that the resistance of this nichrome wire is 75.3 ohms at room temperature, that is 27 degrees Celsius. And it's also given that when it is connected to 230 volt power supply, then the steady current is found to be 2.68 amperes. They also give the temperature coefficient of resistivity alpha as 1.7 into 10 power minus 4 per degree Celsius. Well, now I have to find the steady temperature of this wire. Observe this. Initially, when I connect it to this 230 volt power supply, the current will be something greater than 2.68, because once when current is passing through it, the temperature increases, and hence the resistance of that material also increases. So the current decreases slightly, and they gave the steady current is 2.68. So the initial current, I expect it to be a little more. Now the steady current however is 2.68 amperes, right? And you know the voltage to be 230. By Ohm's law, V is equal to IR. I can say that V by I is equal to R. I get it to be 85.8 ohms. And this is the resistance of the wire at the steady temperature. Some say T. Say T be the steady temperature. And they gave you that 75.3 was the resistance at room temperature. Now, you know the formula that relates the resistivity to temperature. that is rho t is equal to rho naught into 1 plus alpha delta t, right? Now, I know the final resistance is 85.8 and the initial resistance is 75.3, and alpha they gave you as 1.7 into 10 power minus 4. The delta T is T, that is the steady temperature, minus room temperature 27 degree Celsius. Now you have only one variable in this equation, just calculate it. You will get the delta T as 85.8 minus 75.3 by 75.3 into alpha, that is 820 degrees Celsius is the temperature difference. So your final temperature, the steady temperature will be 847 degrees Celsius. This is your answer. Power. You know that power is nothing but the rate of change of energy. Now what is energy? When charge gets multiplied by the potential difference, that is energy. So the rate of change of energy, I mean if I divide this energy with time, this should give me the power, right? I know that Q by T is I, the current. So I can say that power is nothing but current times the potential difference. This is power. By Ohm's law, V is equal to IR. I can replace V by IR here. So I can also write this as power is equal to I square R. And the other way of writing it is V square by R. All the three equations are the same. Now, who is giving this power? Say if you have a conductor here and I put some charges, positive charges on this surface and some negative charges on this surface. There is an electric field established inside and hence the electrons move in this side in this way. Okay, everything is fine. So because of this movement of charges, there is a current inside, but the current won't last forever. As the electrons move here, these positive charges get neutralized, right? And hence eventually the current gets disappeared. So if I want to maintain a steady current, I need somebody who puts new charges on these surfaces as they get neutralized. Actually, these are the guys who give us the power. They are called cells or batteries or whatever they are. These cells and batteries are the ones who give us the power. Now, let's move forward. When I have some resistances connected in series, say I have two resistances here which are connected in series connection. I want to calculate the effective resistance. Now, let me name these points. Say the potential difference across these points AC is V, and let the current that passes through this wire be I. By Ohm's law, by applying Ohm's law to the first resistor, I can say that V across these 2 points AB, V across the first resistor is IR, right? I into R1. And similarly, the potential difference across BC or the second resistor will be IR2. So the net potential difference V is nothing but V1 plus V2. And by Ohm's law, the net potential difference is nothing but the current into the equivalent resistance. And I can write V1 as IR1 and V2 as IR2. This gives me the formula equivalent resistance is equal to R1 plus R2 in this case, where there are two resistors. Similarly, if you have n resistors connected in series, then your formula will be R1 plus R2 plus R3 till Rn. When some resistors are connected in parallel connection, say you have 2 points A and C or A and B. This is one resistor, this is another resistor, and this is another resistor. R1, R2 and R3 connected across 2 points. Say the potential at A is, or say the potential difference between these 2 points AB is V. Now, if I current enters from here, I'll say that I1 current say went through the first resistor, and I2 current went through the second resistor, and I3 current went through the third resistor. The potential between points A and B is V, So since they are connected parallelly, the potential across all these three resistors is V only. By Ohm's law, I can write that V is equal to R1 I1. I applied Ohm's law for the first resistor. Similarly, V is equal to R2 I2 and V is equal to R3 I3 for third resistor. Now, if I want to replace this entire system with one single resistor, then I'll apply the Ohm's law again. The potential difference will be I, which is the sum of all three currents, into R equivalent. That will be the equivalent resistance. Now, I know that I is the sum of I1 and I2 and I3, right? So, I'll just replace the I terms with V by R terms. I can write I as V by R equivalent from this equation, and I can write I1 as V by R1 from this equation. Similarly, I2 as V by R2 and I3 as V by R3. All these B terms get cancelled, and I have the formula as R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3. This is the case when I have three resistors connected in parallel. If I have n resistors, the formula will be 1 by R1 plus 1 by R2 till 1 by Rn is equal to 1 by R equivalent. So this is the formula. Hope everything is clear till now. Let us calculate the effective resistance for this situation. Here I have three resistances connected parallelly, and here I have four resistances connected parallelly. This point is A, this point is B, this point is C. Resistance of all the individual resistors is R. Now, I want to calculate the effective resistance between these 2 points A and C. Effective resistance between these 2 points AB will be R by 3, because three resistors in parallel collection and they are of equal magnitude. You know that if n resistors of equal magnitude are connected parallelly, the effective resistance will be R by n. Check it if you want using the formula. And here you have R by 4, and these two resistances are in series connection, right? So I'll add them up. I'll get my effective resistance to be 7 by 12 R. So this is my answer. This is my effective resistance between these 2 points A and C. And there's one more thing I need to tell you. The effective resistance of a series connection will be always greater than the largest of the individual resistances that are connected in series. I mean to say that if you have a resistance here, say 1 ohm, another resistance here, say 25 ohm, another resistance here, say 13 kilo ohm, the net equivalent resistance here will be obviously greater than 13 kilo ohm, because it is linear addition, right? It's not difficult to get intuition for this. Pick up the greatest one and the effective resistance will be greater than that. But let me tell you one more thing. The effective resistance of a parallel connection will be smaller than the smallest of all the individual resistances that are connected parallelly. Let me explain you. If you have a resistor here and you have another resistor here, say you have another resistor here. If this is 1 ohm, if this is 1000 ohm, and this is 10,000 ohm, the effective resistance, even without calculating, I can say that the equivalent resistance will be less than 1. Just see all the values, pick up the smallest one, and equivalent resistance is going to be less than 1. If you want, you can check it using the formula. That's it for today. Bye friends, keep watching.